Okay, here we go. Problem number 23. Find the probability that when a couple has two children, at least one of them is a boy. How do we do that? Go to a fresh screen here. So number 23. How many children? Oh, two children. Children, probability, at least one boy. Is that what it said? At least one is a boy. Okay. Well, here I am. This is the notes. This is the exam 2 notes. Number 6 has an at least one example. So it says, it does an example. For 4 children, what's the probability at least one girl? Well, the opposite is having no girls. So the answer is 1 minus naught times naught times naught times naught. So that's what we do. The answer is going to be 1 minus naught. Not what? Not whatever they're asking. Not a boy. Times not a boy. We do it twice. Why? I want to make sure this makes sense to you. This right here is the first is not a boy, and the second is not a boy. First not a boy and second not a boy. If the first is not a boy, that's the opposite. This is the opposite. Let me write it right here. This here is the opposite of at least one boy, right? The opposite of having at least one boy is having no boys, right? If you don't have at least one boy, the opposite of having at least one boy is having no boys. And what's the chance you're going to have no boy? Well, the first one's not a boy and the second one's not a boy. So first one not a boy times, and always means times. The second one's not a boy. That's having no boys. But that's the opposite of what they're asking. They're saying, what's the chance of having at least one boy? So I got to take 1 minus that because it's the opposite. That's how you always handle at least one questions. You do by doing the opposite. You do 1 minus the opposite, and the opposite is not what they're asking times not what they're asking. I did it twice because there's 2 children. You see on the example here we had 4 children, so we had 1, 2, 3, 4 knots multiplied, and they wanted at least one girl, so it was not girl, not girl, not girl, not girl, which is no girls. That's the opposite of having at least one girl, so then you take 1 minus it. So that's how you handle at least. You go 1 minus the opposite, which is not the boy, times not the boy, because times is and. All right, so 1 minus, what's the chance of not a boy? 50%. What's the chance of not a boy the second time? 50%. Multiply those in your calculator, you'll get 0.25, so that's 75% chance. Or if you change that to a fraction, your calculator, you just hit the math button and enter. It'll make it a fraction, 3/4. On the TI calculator, if you hit math, enter. Math is located on the left side, third button from the top. Well, 2 buttons below the blue second button, blue, green, and then the math button. Hit math, enter. It'll change it to a fraction. 3/4 is the fraction answer they want. Okay, here's number 24. Here's the data about an individual having a disease, and over here is the test for the disease. Remember, medical tests are not perfect. You can have a disease and the test says you don't have it, even though you really do, or vice versa. So let's talk about the different groups of people here. These 138 people, do you understand what it's saying about them? Yes, they do have the disease, and the test came back positive, saying that indeed they do have the disease. What about those 24 people? yes, they have the disease, even though the test said negative, no, they don't. The test was wrong. It's a false negative. What about these 12 people over here? No, they don't have the disease, but the test gave them a positive result saying they do have the disease. That's a false positive. And then finally, these 126, no, they don't have the disease, and the test correctly said negative, they don't have the disease. Okay, so with that clear, let's look at the question. Find the probability of getting someone who tests positive, given, that's always a very important word, that he or she had the disease. So what do you do with given? So probability of test positive given has the disease. So what's the chance somebody that really has the disease, we're given that they have the disease, they've got it, they've really got the disease, what's the chance that the test is going to come back positive saying that yes, indeed, they do have the disease? Well, for given, the given always goes in the denominator because it's what we know, it's what's for sure, it defines the possible item. So we're given, what are we given again? The person has the disease. Well, who's that? Who has the, who are all the people that have the disease on this problem? It's these two groups, right? Because they're under the yes, have disease. So 138 plus 24. And among those people, how many test positive? 138. So it's going to be 138 over, and then add those in your calculator. What is that? 151, 62, I think, when you add those two numbers. Yeah. And then divide on your calculator to get a decimal. I'm getting 0.852. There we go. So again, given is always the denominator. We're given they have the disease. We're talking about some of these people because it's somebody that has the disease. And out of those people, how many tested positive? 138. Number 25, very similar. Let's make sure we understand. These 20 did not lie, but they got a positive test result on the polygraph test. Lie detector test. It said that it was positive. It said they're lying when they're really not lying. It's a false positive. Whereas these 35, they did not lie, and the test said they did not lie. And then over here, these 43, yes, they lied, and the test positively said they lied. Right? A positive test result says that they lied. And a negative says that they did not lie. We good with that? A positive polygraph test says they lied, and a negative says they did not lie. Okay, so these 9, yes, they lied, and the test said was negative, said they did not lie. They fooled the polygraph. All right, let's put this together then. What do they want me to do here? Find the probability the subject lied, given, that's always big, the test yields a positive result. So probability lied, given, that's positive. So remember, the given always goes in the denominator because that's who we're talking about. That's all possible people. We're given what? That they had a positive test result. So how many people had a positive test result? These people, right? All these people had a positive test result. So that's going to be 20 plus 43. And then out of those people, how many actually lied? Right? Because these are all the people the polygraph test came back positive for, said they were lying. Not all of them really were lying, but all these people, the polygraph test was positive. It said they lied. And among those, how many actually did lie? These people. Yes, lied. The 43 lied. So what probability is that then? 43. What do these add up to be? 63. So divide on your calculator. I'm getting 0.683. 0.683 on that one. There we go. All right, number 26. To reduce laboratory costs, water samples from 4 public swimming pools, it's an important number there, are combined for one test for the presence of bacteria. Further testing is done only if the combined sample tests positive. Based on past results, there is a 0.008 probability of finding bacteria in a public swimming area. Find the probability that a combined sample from 4 public swimming areas will reveal the presence of a bacteria. What are they talking about? So they're basically taking 4 samples and they want us to find the probability that at least one has bacteria. Do you see how this is really an at least one question? At least one. Because they're taking the 4 samples from 4 different public swimming pools and they're combining them for one test for the presence of bacteria. And if even one of those 4 samples, if at least one of them, just one or more of them has bacteria in it, when they test the combined sample, it'll come back positive. And that's what they want us to figure out. Find the probability that the combined sample from the 4 public swimming areas will reveal presence of bacteria. It'll be positive for bacteria. Well, that means this is an at least one question. How do we do at least one? Remember the notes back here? At least one. It's 1 minus naught times naught times naught times naught, whatever they're asking for. If they're asking for girl, it's not girl. If they're asking for bacteria, then it's not bacteria. Does that make sense what I'm saying in your notes there on steps or part 6 on your notes? I'm saying whenever you have at least one question, it's always going to be 1 minus naught times naught times naught times naught, however many, in this case 4 of them, because there's 4 swimming pools, and not what? Not whatever they're asking for. And this, if they're asking for girl, it'd be not girl. If they're asking for bacteria, it's not bacteria. So that's what we're going to do. We're going to go 1 minus naught bacteria times naught bacteria times naught bacteria times naught bacteria. All right, here we go. 1 minus. Now, what's the chance of not finding bacteria? Well, based on past results, there's a 0.08 probability of finding bacteria. So bacteria is 0.008. Is that what it was? Oh, yeah, 008. So then, at any one pool, out one pool. So if you go to one swimming pool, you have a 0.008 chance of finding bacteria there. So what's the chance of not finding bacteria at one pool? 1 minus that, which will be 0.992. That's the chance of not finding bacteria at any one pool. So then that's what we need here. Not bacteria, 0.992, times not bacteria at the second pool, times not bacteria at the third pool, times not bacteria at the fourth pool. Those 4 multiplied together are the chance of not finding bacteria at all 4 pools, which would be no bacteria at all, but we want the opposite. We want at least 1 bacteria, so that's why we take 1 minus all that. So just hit the buttons on your calculator. I'm going to do that myself right now. Save time, you can go 1 minus 0.992 to the power of 4, that up arrow 4, and hit enter. It does the 4th power for you. And I'm getting 0.0316, which rounds to be 0.032 because they want it to 3 decimal places, as they say right here. There we go. Okay, number 27. There is a 0.9982 probability that a randomly selected 27-year-old male lives through the year. A life insurance company charges $187 for ensuring that the male will live through the year. If the male does not survive the year, the policy pays out $100,000 as a death benefit. All right. From the perspective of the 27-year-old male, what are the monetary values corresponding to two events of surviving the year and not surviving? All right, so the value corresponding to surviving. So what happens if the male survives the year, right? Surviving the year. To his bank account is what we're talking about. Well, all that happens is he pays $187 for the life insurance policy. So minus 187. It's minus because he loses that money, right? It's negative on his bank account. He pays out $187 for the policy and gets nothing back because he lived through the year. Now, the second part is better financially, but much worse in the fact that he dies. The value corresponding to not surviving the year. So if he doesn't make it through the year, his family gets a bunch of money. They get $100,000. But minus 187 because he did still have to pay for the $187 policy during the year. So if you subtract those, I'm getting 99,813, and that's positive, not negative, because that's positive money to his family's bank account. They gained almost 100,000. 100,000 minus the 187 policy. If the 27-year-old purchases the policy, what is his expected value? Expected value. How are we going to find that? Well, let's go to the exam 2 notes. So here they are, exam 2 notes. Number 2, gambling or insurance. So here's what we have to do. We have to put in L1 and L2 the dollars winning minus cost to play and the negative cost to play. So, all right, so that's what we need to do. So we're going to go L1. Well, here, I'll just move it over here. So, this is if he wins, so to speak. I mean, he dies, but he wins financially. 99,830. See how it's the winnings minus the cost to play? This is the cost, and this is what he wins. So that's what it's saying here. It's what you win minus the cost to play. That's the 100,000 minus, what was the cost of the policy? 187, which we already figured out comes out to 99,813. So that's the 99,813. And below it goes the negative cost to play, like we have. So these have those upside down. It doesn't matter which one you put in the top and the bottom. The negative 187, that's the cost to buy the policy. So this is the positive if he dies because he gets a lot of money, and this is the negative if he lives through the year. And L2 is the probability of those things. So this is the what's the probability he's going to die? What's the probability he's going to live? It says right here, right somewhere, right there. 9982 is the probability that he lives through the year. 9982. So lives, right there, 9982. Well, then what's the probability it dies? Probability he dies is going to be 1 minus 9982, which is 0018. 0018. All right, so put that in your calculator in L1 and L2. Then hit Stat, Calc, 1var, L1, L2, L1, comma, L2, and then find the mean, the expected value, the X bar. Find out what the X bar is. I'll do it now. Okay, I got -7. That means on average, every one of these policies that people purchase each year, they're going to lose an average of $7 a policy. So expected value, -7. Can the insurance company expect to make profit? Yes, because the insurance company expects to make an average of they're going to make positive. And if the person's going to lose $7, that means the insurance company expects that on average they're going to make $7 on every 27-year-old it insures for 1 year. Every policy it sells to a 27-year-old, it's going to make an average of $7. In reality, it's going to make, $187 on most policies, a whole bunch of them, and every now and then pay out one or two for $100,000, making on average $7 a policy, and which means the insurance policy purchaser loses on average $7 a policy. There we go. Okay, last one, problem number 28. Doctor's mistake, confusion of the inverse. This is a famous question. Here's a question that 95 out of 100 physicians got wrong. It's a famous question. So, suppose that 1% of the population has a form of cancer. The test for cancer is not completely accurate. Let's assume that the false positive rate is 10%. That is, the probability of positive test result, given that cancer is not present, is 10%. So what that's saying is, if you go to the doctor, the probability of getting a positive test result, given that you don't have cancer, right? Remember, given is what is for sure true. We're given, we know for sure that a person goes and is tested. The cancer, they really don't have cancer. What's the chance the test will say they do? A positive test result? 10% chance. 10% chance the test will say you really have cancer when you don't. Because the tests are not perfect. No medical test is perfect. Then the next part, let's further assume, and that's called a false positive. It's giving you a positive result, but it's false. You don't really have cancer. Let's further assume that the true positive is 80%. That is, given that you really do have cancer, what's the chance you're going to get a positive test result? 80%. So we'd hope so. We'd hope if we really have cancer, it gives us a positive result. So let's say a person is randomly selected and tested for cancer. If the test comes back positive, if it says they have cancer, what is the probability that they really have the cancer? The probability of cancer given a positive test result. Now, 95 out of 100 doctors were asked this question, and they thought the answer was around 80%. We'll find out it's really not. It says, hint, make a table with positive, negative test result at the top, cancer, no cancer at the side. So let's do that. So I'm going to come over here. I'm going to make a table. And this is going to, what they say, positive, negative test result at the top. Right, positive at the top, cancer, no cancer at the side. Cancer, no cancer at the side. Okay. And then suppose the total population is 1,000 people and go from there. Okay, so that's going to be down here. That's the total, because this will be totals down here and totals over here. All right, let's give it a try. Let's back up and try from the beginning. So first fact, 1% has cancer. 1% of the total, 1% of the total population has cancer. So remember, we just made up this 1,000. This would work for any number. 1,000 is just convenient. We're just saying, hey, suppose there's 1,000 people who have 1,000 people in the total population. We're going to take a group of 1,000 people. Suppose that our doctor's office in the last year has tested 1,000 people for cancer. Let's just take a nice even number like 1,000. That's the total population. 1% of that total population has cancer. That was the first assumption. Okay, so that means 0.01, right? That's 1%. Of is times. Remember that of is always times. Total population, that's 1,000. That's what we assumed, just to make life easy. We said just suppose total population is 1,000 people to make numbers easy. If you multiply that in your calculator, you get 10. 10 people what? Have cancer. So where's that go? That's 10 people that have cancer. Can it go there? No, that'd be cancer and positive test result. Can it go there? No, that'd be cancer and a negative test result. All we know is they have cancer. We don't know anything about their test result right now. We're just told that 1% of all people in our population have cancer. So 1% of 1,000, 10 people. So that's going to go here, isn't it? That's the total cancer people, right? The total number that have cancer is 10 people. Now we can find this number here, can't we? Because that's the total number of people that don't have cancer. So what's that got to be? 1,000 people total? Minus 10 is 990. No cancer. 990 total don't, out of the 1,000, don't have cancer. Only 10 do have cancer. Okay, now let's go back where we were. Next fact. So next fact is this one. So that is, let's assume that the false positive, that is probability of a positive test result given that cancer is not present. Well, remember, given is what you're focused on. We're talking about people that don't have cancer. Among those, we're given that among those that don't have cancer. Well, who is that first off? Who doesn't have cancer in our little table? The 990. 990. 10% of them tested positive. So 0.10 times 990 is 99 people. That must go right there. Do you see how I came up with that? 10%, right? Given that cancer is not present, given that we're talking about these 990 people that do not have cancer, 10% of them have a positive test result. 10% of times the 990, 99 people, have a positive, right? This is positive. They don't have cancer, but they got a positive test result. Well, then I can find this box again by subtraction, because 99 of the no cancer people, which totals 990, 99 of them got a positive test result. So how many got a negative test result? I can subtract, can't I? So let's do that. That'll be 990 minus 99. What is that? 900, is it 891? I think this is 891. Hopefully I'm getting these numbers right on that. Yeah, 891. Okay. Now, one more fact. Let's look it over. Now they're telling me, this last part, let's further assume a true positive 80%. That is, positive test result given the cancer is present. So among those for which cancer is present, given those kind of people, given that cancer is present, 80% of the time they get a positive test result. So 80% of the people that have cancer get a positive test result. Who has cancer? These 10 people. That's the total cancer number. 10 people. So among those 10, 80% of them, 0.80 times that, which your calculator will tell you is 8, right? 80% of this times, 80% of the 10 people, 80% of those that have cancer get a positive result. So that's 8 people get a positive result. That's right here. Those 8 people, out of all 10 people with cancer, 80% of them, 8, get a positive test result. Well, then 2 must get negative, because that has to total 10, right? Now, finally, we can figure the other totals, can't we? Just add 8 and 99. What's that going to be? 107, and add 2 and 891. That's 893. All right, now we're ready to answer the real question. What is the real question? Here we go. It's find the probability of cancer given a positive test result. Probability, so bring this down to here, of cancer given that the test came back positive. positive. So if you're given a positive test, so given is where we always start, right? We're given that we're talking about some people that got a positive test result. Who are all the people, right? The given's always in the denominator. And it's those that got a test result that was positive. Who are all the people that got a positive test result? It's all these people, huh? It's the 8 and the 99, totaling 107, who all got a positive test result, 107 people. And out of those, how many really had cancer? The 8 really had cancer, the 99 did not. 8 over 107 is the probability that you really have cancer, given that you tested positive. You're one of those 107 that tested positive. The chance you have cancer, only 8 of those have cancer out of the 107. Divide that in your calculator. And I'm getting 0.075. There it is, 0.075. The doctors who were asked this question, 95 out of 100 physicians thought the answer should be somewhere around 80%. In reality, it's about 8%. They're off by a factor of 10. Why'd they think that? They confused the inverse. When they were asked the question, cancer, what's the chance you have cancer given you got a positive test result? They thought it would be about the same thing as positive test result given that you have cancer. That's a switcheroo, right? The cancer goes here, the positive test result goes there. That's inverting, and that matters. The order in which one comes first, cancer, and which one comes after the given, positive. What's the chance you have cancer given you, the test said you do? That's a very different question from what's the probability that you get a positive test if cancer is not present, or I'm sorry, doing the wrong one. If cancer is present, what's the probability of a positive test given that cancer is present? They reversed that. They had confusion of the inverse, which I'm hoping you guys don't have now, that we've carefully worked through this problem. There's only a set. So if you get a positive test result, you still only got a 7.075 chance, 7.5% chance of actually having cancer, even though the test came back positive. Interesting question. Famous doctor mistake question for statistics, one of the most famous.